Hello students! In this video I'm going to be working with you on the first page of 9.4, Dissolving and Dissociating, and I'm also going to sort of wrap up some of the learning that you've done in this section. So let's talk about these three examples and talk about why they dissolve, dissociate, or don't do those things. And let's start with sodium chloride and water, H2O. So we know that water, H2O, is polar because oxygen is more electronegative than hydrogen, so the electrons get shared unequally and they get pulled more towards oxygen. So we have a partially negative side on oxygen and a partially positive side on hydrogen. Well, sodium chloride is not just partially positive and negative, it has a whole +1 charge with the sodium ion, and the chloride ion has a whole -1 charge because they have exchanged electrons. This is an ionic compound. Well, because we have partial positive and negative charges in the water, and partial, well, not partial, whole +1 and -1 charges with the sodium and chloride, definitely sodium chloride will dissolve in water because there is a lot of interactions. There's actual intermolecular forces, really attractions happening between the sodium and chloride atoms and the water molecules. Right? And also notice that not only does sodium chloride dissolve, it dissociates. It splits up into individual atoms. The reason for that is because it really maximizes the interactions here, right? Because this individual atom has a -1 charge, if water can surround that atom, then there's a lot of interactions here between these water molecules and this one negative atom. So sodium chloride and many other ionic substances will both dissolve and dissociate in water. All right, in the second case, we have an example of alcohol. This is ethanol, which is polar, and water, which is also polar. So both of these substances have partially negative sides and partially positive sides. And same thing over here, partially negative side and a partially positive side. So again, because we have some negative and positive, there's going to be an interaction, which means that these substances will be able to dissolve, or actually, because alcohol is a liquid, it's technically miscible, but that's a different thing. The point is they're going to interact. There's going to be some intermolecular forces here. Now, alcohol, is it going to dissociate? Well, it doesn't really make sense for these atoms to split up into individual atoms, like in this case, right? Because that's not going to allow for more interaction between positive and negatives, right? Just having them um, having the alcohol molecules separate from each other and then having them interact with the water, that's good enough, right? It doesn't make sense for these to split into carbon and hydrogen and oxygen atoms individually. It's not gonna benefit us. So something that we see here is that whenever there's positive and negatives, there's gonna be dissolving. So we can sort of say this like dissolves like. Things that are similar are going to dissolve in other things that are similar. So polar and polar, they are definitely alike. They're going to dissolve. Ionic and polar, even though they're different, they're similar in that they have these positives and negatives, so they're also going to dissolve. But if we look at oil here, which is composed of only CH bonds, oil is non-polar, so it does not have any positive or negative side, whether it be partial or a full positive negative charge like sodium chloride. So it doesn't really interact with water, right? There's no attraction between positive and negatives, so they stay separated, right? Oil and water are not alike. They can't really form intermolecular forces, so they don't dissolve. So again, the big idea here is like dissolves like. All right, let's just record some of those key ideas in our notes. In salt water, we have an ionic solute, and then water is our polar solvent. They dissolve, they interact, they dissociate because the sodium and chloride atoms split up, and also it conducts electricity. right? We need something to dissociate into positive and negative ions to allow electricity to flow through that water, right? So if you remember in that very first video that we saw in 9.1, pure distilled water, did it conduct electricity? No, it did not. So water itself is not a good conductor of electricity. We need to have ionic things dissolved in water for water to conduct electricity. Now, most water in the world does have various ionic things and non-ionic things dissolved in it. So tap water, river water, all that water is going to conduct electricity. But water itself does not. It needs to have something ionic dissolved in it. All right, sugar water. We've got our polar solute sugar, our polar solvent, water. Like dissolves like. We've got positive and negative. Yes, they dissolve. But no, they don't dissociate. Only ionic things dissociate, not polar things. And because they don't dissociate, it does not conduct electricity either. So sugar water will not conduct electricity. Okay, oil and water. Well, oil is nonpolar, water is polar. Like dissolves like, but these are not alike because nonpolar things don't have any positive and negative sides. So it will not dissolve, it will not dissociate, it will not conduct electricity. All right, now that's a good summary, but we're going to go just one step further. We're going to actually talk about if something dissolves or dissociates, we're going to write that out as an equation and then write the number of particles that we get from that. So we're just going to go one more step, and that's kind of where we finish with this module, okay? So this again is on page 1 of your worksheet on 9.4, and then page 2 looks just like this, and you have a chance to practice this, okay? Now it's really important that you're able to identify whether something is polar, nonpolar, or ionic for this worksheet. And we've learned that previously, but you may have to go back and review some of that if you don't know how to tell. So CH4, hopefully you remember how to figure out if something is ionic, polar, or nonpolar. If you don't, look back. But this guy is nonpolar, so I'm going to write NPC. It is nonpolar covalent. That C stands for covalent. Okay, as we saw on our previous slide, nonpolar things do not dissolve and they do not dissociate. Now, in terms of this number of particles, that's really only going to be relevant if it dissociates. Because if it doesn't dissociate, it's just going to stay as one thing. So before we actually reveal this, let's look at the equation. Now, we're going to start as CH4, which is methane, and there's a G here. That G stands for gas, right? We're actually going to write the chemical equation, which we have done way back in quarter 1, not for a while. This one's pretty easy though, because it doesn't dissolve, the same thing. It's still going to be methane gas. It's not really going to dissolve. It's not going to change. How many particles do we have here? Well, by particle, we want to look at molecules, right? Of course, we have 4 hydrogen and 1 carbon, but these are all bonded together into one molecule, one particle. So, one particle, right? We had 1 particle before, 1 particle after. Okay, let's look at CH3OH, which is methanol. All right, because of that OH group, this is going to be polar covalent, PC. We know that polar things dissolve in water and they do not dissociate. So when we write the equation, it's going to be very similar to this previous equation, but with one little difference. We're going to start by writing our original substance, CH3OH, with an L this time, which stands for liquid. Then we write our arrow. Now, it's going to stay the same substance. However, we're going to change the state of matter, and we're going to write AQ for aqueous. So aqueous just means that it's dissolved in water. That signals that it's having these types of interactions here that we see between substances when they're dissolved. So it's not breaking up into individual carbon and hydrogen and oxygen atoms, but it is interacting with water, and so we write AQ for aqueous. But how many particles do we have here? Well, again, just like in the previous case, our molecule here is staying a whole intact molecule. It's not splitting up individual atoms. So we had 1 molecule before, and we have one whole molecule after. So there's going to be a 1 there, okay? All right, next one we have magnesium chloride. Now, magnesium is a metal and chloride is a nonmetal. We've got a positive ion and a negative ion. This is going to be ionic. Okay, we know that ionic things dissolve and dissociate into water. So this is where writing the equation gets a little bit more complicated. So we're going to start with our same kind of thing. We have magnesium chloride with an S. That S stands for solid. It's originally solid. Now we put it into water, but it dissociates. So these are going to split into individual atoms. Now, if we have one MgCl2 molecule, within that, how many magnesium atoms are there? Well, since there's no number here, there's an invisible 1. So there's going to be just one magnesium atom. And we're going to actually write the charge because this becomes a magnesium ion when it splits apart and dissociates in water. So we have one magnesium 2+ ion. All right, I know it's been a long time since we've dealt with charges of ions. You may have to go back and review that. It's not essential that you memorize that because this is not a huge emphasis right now. But technically, we do want to write that charge on the ion. All right, and then within this one molecule, how many chloride ions do we have? Well, we have 2. So we actually need to write it like this with a big 2 here to show that there's 2 of these chloride ions. Remember that these little numbers here indicate there's 2 chloride ions within this molecule. But here, there's 2 chloride ions and they're separated. They're not going to be bonded together anymore. And because they're separated, the 2 is going to go in front. So, and we still have to write the AQ in aqueous because these are interacting with water, right? They've dissolved. Anytime it dissolves, we want to write AQ for aqueous. If it doesn't dissolve, then we can leave the state of matter the same as before. So we started with 1 particle of magnesium chloride. How many particles did we end up with total? Well, 3, right? 1 magnesium ion and 2 chloride ions. Now, writing the equation is not going to be something you're tested on, but it is good practice to write that equation, and you need to figure out how many total particles we had. Just one more hint, right? Occasionally you might see some examples of a substance that has a polyatomic ion. So, for example, maybe you have something like, let's say potassium nitrate, right? KNO3. Right? On the back of our periodic tables, we always have those list of the polyatomic ions. Well, potassium nitrate is going to dissociate because it's ionic, right? We've got a metal and we've got a group of nonmetals, which are a polyatomic ion. So this is going to dissociate. How many particles are we going to get from this? Well, we have a lot of things going on here. Potassium is definitely going to separate. Is this going to separate? Well, no. The polyatomic ion is going to stay together. So if we were to put this into water, it would dissolve and it would dissociate into 2 different particles, 1 potassium and 1 nitrate. So that just gives you a hint because some of the examples on your practice do have polyatomic ions. Okay? But again, big idea here is that like dissolves like, right? Both ionic and polar have positive and negative parts. They like to dissolve in each other. Only ionic dissociates. Only ionic splits up into individual atoms. Nonpolar molecules don't have positive and negative parts. They don't interact with water. They don't form intermolecular forces. They don't dissolve. All right, hopefully that helps you get started on your worksheet. Good luck.